Hey guys, welcome. Yeah, so in this video, we're going to talk about the alternating series test. And the alternating series test comes with what's called a truncation error. And I'll talk about the truncation error in detail in the next video, but I'll give it a brief mention at the end of this video. As this is example 0, we're going to talk big picture, yeah? Okay, all right. So let's get on with it. So this is what the alternating series test says. If for an alternating series this, the following two criterion are met, and the first of them is this, which is that the absolute value of a sub n plus 1 is less than the absolute value of a sub n for sufficiently large n, meaning this doesn't need to be true at the start, but needs to be true somewhere down the road. And of course, this is saying that the series has a decreasing sequence in a sub n, right? That's what this is saying, right? If this is true and this is also true, and this is, notice, equivalent to the divergence test. But yeah, if this is true and this is true, then the alternating series converges. And as I said, here's a note on the fact that this first criterion needs to hold true only for sufficiently large n. Yeah? Okay, cool. All right, so this is all that the alternating series test says. It's not complicated. But yeah, let's talk more about it. Now, a very famous example of an alternating series that converges is the alternating harmonic series. And I dedicate a different video to showing what value the alternating harmonic series converges to, and I'll link that video below this. And the value to which the alternating harmonic, which is this here, converges to is the natural log of 2, which is roughly 0.69. Yeah? Okay, cool. Now, let's use then the alternating series test to see why the alternating harmonic converges. First, we put it through the first criterion, which is we look at the absolute value of a sub n and the absolute value of a sub n plus 1, which are this and this respectively. And clearly 1 over n plus 1 is less than 1 over n, meaning the first criterion is met, right? Okay, and then it's pretty easy to see that the second criterion is also met. And therefore, we say by the alternating series test, the alternating harmonic converges. Yeah? Okay, so that's it. This is how you apply the alternating series test, yeah? Okay. All right, but let's say a little bit more, which is let's get a feel for why this has got to be true. And let's do so by considering partial sums. But first, let's kind of get a feel for what the terms of the alternating harmonic look like. They look like this, right? Obviously, they can continue on ad infinitum, right? Okay. Now, if we look at the kth partial sum, when k is equal to 1, we'll get S1, right? And that's just 1, right? 1 over 1 or 1. And then S2 is going to be 1 minus 1 half, which is a half. And notice that S1 is greater than S, S being the value to which the alternating harmonic converges, which is a natural log of 2 or approximately 0.69. And so 1 is clearly greater than approximately 0.69. Whereas S2, which is 1 half, is less than the natural log of 2. And then S3, right? S3 is going to be bigger than S, or the natural log of 2, for, again, the alternating harmonic. And then S4 is going to be less than S, or the natural log of 2, right? Yeah. Okay, so you get a feel for what's happening. And as I said already, we know that the alternating harmonic converges to the natural log of 2, roughly 0.69, yeah? Okay. So this is what's happening, which is that the partial sums are bouncing around the value to which the alternating harmonic series converges. And more generally, for an alternating series that converges, this is kind of the visual. If S is the value to which that alternating series converges, this line here, then S1 will be either above or below the true value. In this visual, I have S1 above, right? And then S2 will be then on the other side, but closer to S. And then S3 will bounce back on the other side, but even closer to S, and so on. You get it. And so then by continuing on, the partial sums get arbitrarily close to the true value S to which the alternating series converges. And so yeah, this is it for the alternating series test example 0. And the truncation error is this, which is that like if we use the kth partial sum to approximate S, which is that like if we use finitely many terms of a convergent alternating series to approximate the value to which it converges, we can say how good that approximation is. So if we approximate the value of S by the kth partial sum, we can say how good that approximation is. And that's what the truncation error is about, yeah? And as I said, the next video will be on that truncation error. Okay, otherwise, I hope you enjoyed this video and keep watching. Take care.